This is Larry Benko, W0QE, and this video is about antenna plus transmission line impedance. And we'll lay the groundwork to a follow-on video about a question that has puzzled me for years. In this video, we will look at some of the features that separate SimSmith from other analysis programs and how these features can provide insight into the world of RF. SimSmith is a linear, time-invariant circuit analysis program that normally shows impedances on the Smith chart, and nearly everything is adjustable in real time. I think a lot of users don't initially appreciate how valuable the real-time adjustment feature is. Furthermore, components are allowed to have values that vary with frequency based on a file input. SimSmith supports file formats from several different programs, and for more information you can go to Help and the Primer, and on page 15 of the Primer where it says Load here is some documentation that talks about different file formats that are available. And it's pretty flexible. If I go back to my little list of data files I have here, I can show some quick examples. The first example is just a text file that was created from the AIM 4170. And it looks fairly easy to decode. SimSmith looks for this line right here. And the first item in the line is the frequency. The second item is SWR, which SimSmith ignores. And then R sub S, X sub S, and it uses those. And these other numbers it ignores also. And it reads line after line after line, each line having one frequency's worth of data on it. What's up here is just a header. And it does that quite well. Similarly, here's an EasyNet file. It looks for this line and reads the data also. And it does, I don't know what other file formats it supports. They may not all even be listed in the primer. But typically what I do, if I want a simple file, I'll create something like this manually. I can put comment lines up here. The file can be named anything you want. I usually use something like text or .asc for ASCII or .csv or .dat, etc. But I just use this format, freq, R, X, and put my data in there, and it reads that format just fine also. I don't know if that represents some format that a program uses, but that works just fine. I've used that for a long time. And if my comment lines confuse SimSmith, I can just start a line with something like this. The double slash tells SimSmith to ignore the line. And finally, there's another one here. I might make a quick comment about the fact if I open this, what will happen is Excel will come up because Excel is assigned the .csv suffix, and it comes up automatically. But I can also look at this as a text field, as a text file too. We can see they're basically the same. But again, SimSmith reads this format just fine too. So if you have a program that you're questioning whether SimSmith can read or not, my suggestion to you would be just give it a try. And if it doesn't work, look at the file a little bit, and you might be able to just delete a little bit of a header or something and get it to work and be off on your, on your way. Since the topic of this video is antenna plus transmission line impedance, let's start with an antenna. Now we could have scanned an antenna either at the feed point, or we could have put a piece of transmission line in series with the antenna, scanned it here, and then gone backwards to calculate the antenna feed point impedance if we wanted to. But we don't need to do that for this purpose. I've created some files in EasyNet, and they're not going to be perfect impedances compared to what you put up outside. But what I'm trying to show, it really won't make any difference. They'll be pretty close. So let's look at a 66-foot, 12-gauge wire, 40-foot high flat top dipole. This is the locus of impedances we get. Now this file was created from 1.7 to 30 megahertz, which is our sweep range here. We're in the sweep mode. If we leave it in the path mode, we only show the individual impedance at the frequency. And if we come over here and Okay, that's already set to be linear. Let's just leave it there and say, and I'm going to scroll this up and down and watch where it'll move. The point will move. We'll say move with frequency. But if we put it in sweep mode, then SimSmith is actually moving the frequency and drawing a line in between the points. So here is the impedances possible from that antenna at the feed point. Now what happens if we put a piece of transmission line in series with this antenna? Well, clearly things change drastically. And to be able to compare things, I'm going to make the velocity factor of this piece of transmission line 1 for the moment. Not for any particular reason, but mostly just for the standpoint I want to be able to compare electrical length with electrical length. So we'll call it velocity factor 1, and we'll say it's 70 feet long. So that's 181 degrees of length at 7 megahertz. And again, it really doesn't matter what length we use. What we see though here is two things. Here's the original antenna, and here's the antenna after we put the piece of transmission line in there for all the frequencies. So this is an awful busy circuits, or awful busy graph. So let's go back here and start this at 0. Of course, with 0 length of transmission line, we're looking right here. We're looking at G. Looking at T1 gives you the same thing as G. But we're looking at the generator. And if we add 1 foot of transmission line in there, look how much change we get. 2 feet, 3 feet. Now we start seeing this part of the loop move faster. And that's because these are higher frequencies. These higher frequencies will move faster than these because a fixed length of line is a longer electrical length at higher frequencies. So as we continue to add length, what we see is we see the graphs start to occupy a huge amount of the Smith chart. There are still a few places here where the SWR is kind of low, 22 megahertz and 7. That's to be expected. It's a 40-meter dipole, and the third harmonic it works pretty well on. So that's all believable. What would happen if we did not put a piece of 50 ohm transmission line here, but we put a different impedance here? I'm going to make these linear adjustments again, just from the reason that it's easier for me to talk and mess with this at the same time. So let's go back here again to something small like a couple of feet. There's a 2 foot change with 50 ohm line. As I increase the impedance of the 50 ohm line, look what happens. I start to move back up. I start to move up where I don't have much rotation compared to no transmission line. So let's continue this. Now, I hope everybody's getting the idea here, but this is pretty cool. If I use something like 500, 450, 500 ohm line, all the impedances that this antenna could possibly be here, transformed through whatever length transmission line I have here, I end up with something that's only in part of the Smith chart. So let's continue with the length here. And it moves around. And what we're going to see, though, is eventually, there's a reason it moved the way it moved. This right down here, this area right here, let's look at the frequency out here. It's 4 megahertz. Here it's 5.3. If we say we're just not going to use this antenna below 5.3 megahertz, all these impedances back here are in a pretty small area. So let's move this up to say 5.3. Maybe let's say 5.5 maybe. They're in a pretty small area. That means if I need to make a matching network here, it doesn't need to be nearly as complicated as a matching network that can occupy the entire range of the Smith chart. So you say, well, that's nice, but I really want to have 80 meters. So what we need to do here is increase the length of this wire some. And remember that SimSmith knows about impedance of the antenna. It does not know about the pattern. It does not know anything about polarization or anything like that. That's a different issue that you have to use another program, obviously, to calculate. But if we're looking at getting power to the antenna, SimSmith is really good at doing that job. So from 66 feet, the next one I put in here was 88 feet. At 88 feet, now we see, and let's go back to 1.7 megahertz here again. Again, we're going to fail it down there. But now, right here, we're at about 4.5. So 4.2. So to use 80 meters on an 88-foot antenna, we have to include this area. We have a bigger area of the Smith chart that we need to match. And again, we can look at this as we increase the line length. But all the higher frequencies, notice all the higher frequencies of the graph here stay nicely contained over here. It's just the bottom edge that gets out of bounds. So once again, increase the number again. Now I've picked what books typically use as conventional numbers for different types of antennas. And people over the years have figured this out. But SimSmith shows this in a really nice way. And I hope that everybody who watches this is appreciating the fact that you could easily make one of these graphs manually on a piece of paper with the impedance data you would have in this file. But to be able to take something like this and do what I'm doing right now by rotating this, every time I click here, you might as well add an hour's worth of work. It would be an incredibly tedious job to do that. So, this is the power of SimSmith. So if we look at something like this and say, where's the frequency over here that we can go down to? We're at 3.8 megahertz. We could stretch that probably to 3.5, be okay. So 105-foot dipole, we can make work on 80 meters. And this is for lengths, most normal lengths would be fine. So you might want to go up a little bit higher. I don't know. Let's say we made it 120-foot dipole. Now, what does the frequency say over here? 3.3. Here, let's do this. We can do two things here. We can put a marker if we want, and that's another feature SimSmith has. You just drag this anywhere you want, and then just type the frequency in here, and it'll move to wherever. So we want to go down to this frequency, and this is 1.7 down here. So we just need to watch where this goes as I add length to this. 3.5 megahertz stays everywhere. It always stays in. It's pretty well behaved. And this whole plot is in a small area of the Smith chart. And this is an extremely powerful thing, and it's going to be something we're going to use in the next video that's very interesting. One more thing before we wrap the video up, and that is how much loss is actually occurring in the transmission line here, assuming we have a impedance matching device here, such as a tuner. And we can calculate that in SimSmith very, very easily. We need to change the generator type in SimSmith, which is right now what they call UZ0 generator. And that means the generator is a 50 ohm output impedance. And this is a bad match to 50 ohms, so we're going to get what's called mismatch loss here. And if you're unfamiliar with that term, you can look it up in Wikipedia, but it's like an opportunity loss. The transmitter could generate more power than the impedance affords it. And that's why we put a matching network in here. So to alleviate that problem, SimSmith has a mathematical matching network built into it. And that's a function called XMatch. For that generator type XMatch, we have a matching network here, shown with the M, which affords us the 100% perfect tuner you can get. And then all the power after that we can calculate as being loss. So doing that, and we can, right now, this is a 1 watt generator. We want this to be something else. We can set this to be, say, a 100 watt generator. It's 100 watts now, and we see that at this frequency, we get 94.97 watts at the antenna. But we don't want to sit here and grind through all the numbers like this and have to calculate the loss at each time and see what's available. Let's sweep it and see what we get. So we're in the watt mode here. So we need to $100 watts is at the maximum here. Let's go there. So here's 55 to 100 watts. And this is the power delivered into the antenna. And this is the power over frequency. And SWR is shown here on the line, but that's really not important. Let's just get rid of it. This is the actual power. So if we take this 120-foot, now you can't read this very well, but if you hover over this, the data that's there will appear right here. So as I hover over it, we see that's still a 120-foot antenna. So the 120-foot antenna has more than 90 watts delivered to it at all frequencies down through about 3.4 megahertz, which is kind of interesting. If you're more of a dB type person, we click here, we can get dB delivered to the load. Now remember that 100 watts is a plus 20 dBm signal, so we have to set our scale differently. That's the center point, and I'll go down like this. And I've done some videos on scrolling around on the axes in the square chart. But here's a 1 dB step. So if we say right here, half dB steps, we say we're going to allow half a dB only of loss in our feed line. We can achieve that with 500 ohm open wire feed line from 3.4 megahertz, 3.4 up to 30 megahertz. Now, let's look at that compared to, and I'm going to do a little bit of another feature here in SimSmith. We're going to create another generator in the load block. This load block here has a new generator in it, just like this one. It has the same impedance that this one has, so it's exactly the same circuit. And if I was to put the same piece of transmission line there, we would have one impedance at T1 and one at, we're talking about power. We'd have one at load and one at LG1. So LG1 you see is a purple trace, and it's on top of the red trace. They're identical. Let's make this piece of transmission line for the moment 50 ohm transmission line and see what the difference is. Now 50 ohm transmission line has a velocity factor of say 0.66, and we still need 70 feet to get to the antenna, so it's an electrically longer length. It's 269 degrees versus 195 at 8 megahertz. And it's got higher loss. Even big coax has probably about 3 dB. RG8 coax, let's use RG8 for right now. RG8 type coax is about half a dB per 100 feet at 10 megahertz. Big quality stuff, hard lines getting to be 0.2, 0.25. But let's compare the two of these graphs right now. And there's the difference. Now, if somebody tells you that open wire line always has lower loss than 50 ohm coax, they'd be lying to you, because right here we see less loss in this transmission line than we do in the open wire line. The open wire line one is red. The purple one is the 50 ohm line. But most of the places we see the open wire line beating the 50 ohm line by quite a bit. When the 50 ohm line wins, it wins by a fraction of a dB. When it loses, it's 2.5 or 3 dB. Now, this may not seem to be drastic enough for you. So we can go down here to pick a smaller piece of smaller horizontal length for our dipole and load that. And now we start to see even bigger changes. I'm going to have to change the scale here now. Oops, changed it the wrong way. 1 dB per step again now. So with a 105-foot dipole, if we used 50 ohm transmission line, and here the open wire line is less lossy than the 50 ohm line everywhere. But here we have over 7 dB of loss at say 10, 11, I don't know, about 11.2 megahertz. So this is an incredible number of calculations going on here at the moment. But as long as we stay with the open wire line, our losses are low, everything's good, and we should be able to afford ourselves a pretty easy match to that smaller range of impedances. Let me wrap this up right now saying that the next video is going to be on the Johnson Matchbox. The Johnson Matchbox was a tuner that was around when I first got licensed, And as a kid, I never had the money to be able to afford one, but everyone who had one thought they were absolutely great. And they were highly revered, very expensive on the used market and stuff. And I got a hold of one 30 years later, and I thought it was a piece of junk. And with a matching device, such as a tuner, your perception of the tuner is related to whether you can match or not. It doesn't mean that the tuner is junk. It just means what I was trying to do with the tuner was not its forte. So I'm going to analyze the Johnson Matchbox next time in excruciating detail. I got one from a friend of mine who was willing to let me tear it apart, make a whole set of measurements inside, put it back together, and then see if the SimSmith matched what the actual matching range was, and it did quite well. And show how that fits very nicely with a reasonably sized dipole fed with open wire line, which is what people were doing when I was a kid. Anyways, hope everyone's enjoyed this video. And there's just a huge amount of things that SimSmith can be done to calculate problems, solutions to problems, and things that we run into regularly, and can help give us insight into a lot of these types of problems. Thank you very much.